Welcome to my presentation on the T0 model as a more complete theory compared to approximative gravitational theories. I am Johan. Today, I will explain how the T0 model offers a more comprehensive framework for understanding quantum gravity, with other theories serving as mathematical approximations. The search for a theory of quantum gravity remains one of the most significant challenges in theoretical physics. Multiple approaches have been developed, each with distinct mathematical frameworks and conceptual foundations. The T0 model offers a fundamentally different perspective. Rather than viewing various gravitational theories as competing, we can understand them as mathematical approximations that capture different aspects of a more fundamental theory, the T0 model of time-mass duality. In this presentation, I will examine how string theory, loop quantum gravity, asymptotic safety, causal dynamical triangulation, and emergent gravity can all be understood as partial approximations of the more comprehensive T0 model. The T0 model inverts the traditional relationship between time and mass. Instead of relative time and constant mass as in relativity theory, it postulates absolute time and variable mass, mediated by the intrinsic time field T of x and t. The cornerstone of the model is this intrinsic time field, defined as T of x and t equals h bar divided by the maximum of m of x and t times c squared, or omega of x and t. This elegantly captures both extremes of physical reality, mass-dominated systems and wave-dominated systems. From this field, gravitation emerges naturally. The gravitational potential is defined as phi of x equals negative natural logarithm of t of x and t divided by t0. For a point mass, this gives us phi of r equals negative gm divided by r plus kappa times r. The linear term kappa r naturally explains galactic rotation curves without dark matter and cosmic acceleration without dark energy. String theory replaces point-like particles with one-dimensional strings whose different vibrational modes represent different elementary particles. It typically requires 10 or 26 dimensions and automatically includes a gravity-like interaction. From the T0 model perspective, string theory can be understood as an approximation that captures certain aspects of the intrinsic time field dynamics. The additional dimensions could be interpreted as mathematical tools for describing the complex behavior of the time field in high-energy regimes. The various vibrational modes of strings could represent different manifestations of how the time field interacts with matter and energy. A common misinterpretation is that extra dimensions physically exist as extensions of space. The T0 correction shows these dimensions are mathematical constructs modeling the time field behavior without recognizing its fundamental nature. Loop quantum gravity quantizes space directly by representing it as a network of discrete volumes and areas. In this approach, space itself has a discrete, granular structure at the Planck scale. From the T0 model perspective, LQG can be understood as an approximation that captures certain aspects of the intrinsic time field in a discretized form. The spin networks could be interpreted as discrete approximations of the continuous time field dynamics, similar to how one might approximate a vector field with a lattice grid. A common misinterpretation is that space is fundamentally discrete and granular at the Planck scale. The T0 correction suggests this apparent discreteness is an artifact of approximating the continuous time field with discrete mathematical structures. Space itself remains continuous, but the interaction of the time field with matter creates preferential scales. Asymptotically safe gravity proposes that naively quantized gravity is stabilized at high energies by a non-trivial fixed point in the renormalization group flow, allowing the theory to have a consistent high-energy limit. From the T0 model perspective, this fixed point could be interpreted as a mathematical manifestation of the beta t equals 1 parameter. The high-energy stability could be seen as a special case of the more general time field dynamics. The equation limit as E approaches 0 of beta t of E equals 1 in the T0 model defines a natural fixed point, conceptually similar to THE fixed point in asymptotically safe gravity. A common misinterpretation is that quantized geometry is the correct approach, merely requiring proper handling of renormalization. The T0 correction shows that fixed points in the renormalization group flow are mathematical manifestations of more fundamental parameters in the T0 model. Causal dynamical triangulation approximates curved spacetime through triangulation and simulates quantum gravity through statistical summation over all possible triangulations. From the T0 model perspective, This can be understood as a numerical method to approximate the continuous time field dynamics in complex situations. Emergent gravity approaches view gravity not as a fundamental force but as an emergent phenomenon. These approaches correctly recognize the emergent character of gravity, as proposed by the T0 model. However, the T0 model specifies exactly the mechanism of emergence through the intrinsic time field. The T0 model's formula f vector of x and t equals negative gradient of t of x and t divided by t of x and t provides a precise mechanism for how gravitational force emerges from the time field gradients. In conventional quantum mechanics, we use statistical descriptions like wave functions and probability amplitudes because we lack access to the underlying dynamics. Similar to how thermodynamic laws represent the statistical description of many particles, quantum mechanics itself might be a statistical approximation of a deeper reality. In the T0 model, this deeper reality is described by the intrinsic time field. The modified Schrödinger equation in the T0 model is I times h bar times t of x and t times partial derivative of psi with respect to t, plus I times h bar times psi times the square bracket containing partial derivative of t of x and t with respect to t plus v vector dot product with gradient of t of x and t equals h hat operating on psi. This contains the conventional Schrödinger equation as a special case when the time field is assumed to be constant. This perspective offers a natural explanation for phenomena such as quantum decoherence and the measurement problem. The T0 model can be viewed as a metatheory, or framework theory, that unifies various approximations, explains the success of approximative methods, resolves conceptual tensions between quantum mechanics and relativity theory, and provides ontological clarity. This metatheoretical status is similar to how relativity theory provides a framework that explains why Newtonian mechanics works at low velocities while revealing its limitations. The various gravitational theories could be understood as limiting cases or approximations of the more comprehensive T0 model, each valid in specific regimes: string theory for high-energy quantum phenomena, LQG for discrete spatial structures, asymptotically safe gravity near the UV fixed point, causal dynamical triangulation for numerical approximations of complex geometries, and emergent gravity for macroscopic scales. The T0 model provides a more complete, fundamental description of reality, with other gravitational approaches representing mathematical approximations valid in limited domains. The intrinsic time field provides a unifying framework that can accommodate aspects of various quantum gravity approaches within a single coherent structure. This perspective has several important implications. Rather than viewing different approaches as competing theories, we can understand them as complementary approximations. Our ontological assumptions may be more influenced by our mathematical tools than by the underlying reality, and experimental efforts should focus on detecting phenomena where the T0 model makes distinct predictions. Even the T0 model itself should not be viewed as the final word in physics. Like all scientific theories, it represents our current best attempt to understand reality but remains a human construction that will likely be refined or extended by future insights. The most valuable contribution of the T0 model may ultimately be its demonstration that a more unified and coherent description of physical reality is possible beyond the fragmented approaches of conventional quantum gravity theories.